Good morning. I'd like to begin with something of the background. There's been a good deal of work accelerating in recent years on categories equipped with differential structure. And one usually gives a bunch of axioms, and normally one has a standard model in mind. For example, the smooth functions. Then the question arises from a logical point of view, whether the axioms are enough. They're no doubt true in your standard model, but are there any missing axioms? So that came to interest me, and a natural place to start is just traditional partial differentiation to see if the usual rules there are complete. Usual rules are equational, so it's natural to think of equational axiomatization. So let's have a quick look at ordinary equational logic just to start off. Here we are. So we have operation symbols of RTN. We build up our terms or expressions the usual way. If we don't like if we don't like prefix notation, we might use infix notation. A bunch of axioms, and then we have a logical system. We can assert any axiom. We have the usual rules for equality, reflexivity, symmetry, and transitivity. We have the congruence rule, and since the assertions are universally quantified implicitly, we can do substitutions, and that gives us theorems indicated by the usual theorem sign. How does that work with partial differentiation? Well, we have to get our notation right first. So there's a lot of odd things that go on with notation of partial differentiation from the point of view of type theory with its discipline of free and bound variables. Here the discipline is somewhat flouted. Well, one thing that happens, not quite that, is that you might write df by dx and say where f is some function f of x, y. So the separation isn't good, and it'd be better just to have it all in one notation, f of x, y by dx. And a good notation, logically a conventional notation would be something like de naught by dx. That's meant to be the partial derivative with respect to x. That's a function, and you apply it to E1. There x is bound, and that's that. Then one can use that to make sense of the actual notation normally used. For example, de by dx, in that x is both bound and free, because that's the function de by dx at x. So in our notation there, the x occurs twice, once bound and once free. But still, we can use the ordinary notation because it just is now an abbreviation for our more standard notation. Another one like that is de by dx, where x is E1. And there's two occurrences of x, they have to be the same. So the x to the left, although bound, you can't change it. So that's all a bit strange. But we just regard that an abbreviation for de naught by dx at E1, applied to E1. So we're allowed to use it. And just like one uses infix and has an official notation, our official notation is going to be pdiff of two things. The first thing is an abstract, x dot E naught, and the second thing is an argument. So that's just a way of writing officially the notation de naught by dx applied to E1. So we're outside the bounds of standard equational logic because we have operation symbols here, pdiff, which apply to abstracts, not just arguments. So let's see what our syntax is for our partial differentiation algebra. We're going to allow real constants, variables, plus and times, f of some e's, where f is actually a function variable. So we now have two kinds of variables, ordinary variables and function variables. Function variables come with built-in aritays and pdiff. And if we're going to do equational logic, we need substitution. So here's a standard substitution. There's nothing special about it. You just, in substituting into pdiff, you have to be careful that free variables don't get captured. And that at the bottom is the same definition, but using one of the notations, the Leibniz one, de naught by dy, where y is E1. But we also need to substitute for function variables, and for functions, we need to substitute not expressions, but abstracts. So for function f of RTN, we substitute the abstract x naught through xn minus 1 dot e. And these are the equations for it. The first and third are easy to explain. Well, the first one is just if you substitute into a function application, you substitute into the bodies of it, as long as the function application is not that of the function you're substituting for. If it is, you get to the second line, So there again, you substitute into the bodies, but having done that, you must use the definition of f that you've been given by the substitution. So you must give as a result E, where the x's are replaced by the e's themselves having been substituted. So that's what gives you the expression on the right. And for pdiff, you just go past it, being careful not to have any variable capture. Okay, logic is just what you'd expect, same as before, but you add on some things for the new kind of operation symbol. So the obvious congruence rule, and as well as ordinary substitution, we're allowed the functional substitution that was just defined, and we get theorems as before. Obviously, this is part of a more general pattern, which I'm not spelling out here because there's not enough time, but I recommend you read these references by Fiore and her and Mahmoud, and they spell out these things in generality. They use different notations from me, but it is entirely equivalent. One of these references is ordinary equational logic of the kind we just mentioned, well, ordinary binding equational logic, ordinary second order equational logic. The other is the multi-sorted one, which is a fairly standard variant. Okay, so what's the axioms going to be now? We've got the formal system. We're going to have 4 axioms. Well, apart from obvious axioms of commutative rings and addition and multiplication tables of the reals, the first 2 just tell you how to differentiate a plus and times, which we all know how to do. The last one just tells you that it doesn't matter what order you do partial derivatives in, it's the same, dx by dy is the same as dy by dx. The third thing is the chain rule for exactly one case, for the case of binary functions, f of applied to g0 and g1 applied to x. And it's the usual chain rule that one has there. And originally I had the Unary chain rule, but Sam Stason suggested I could get away with the binary one, and I'm grateful to him for that suggestion. So let's see what the consequences of, or some consequences of these axioms are. One easy consequence is to set y equal to 0 in the first 2 axioms. That gives you dx by dx is 1 and d0 by dx is 0, which will both be useful. So let's look at another example theorem. Let's take the unary, the constant in the unary versus the chain rule. Let's just look, for example, at the constant one, dy by dx equals 0. And I want to show you how you get that from the binary chain rule. So there's the binary chain rule rewritten. What we're going to do is we're going to take f to ignore its arguments and just return y. So we substitute x0, x1 dot y, that's abstract for f. I want g0 to ignore its its argument and just return 0. So g0 of x is going to be 0, the same for g1. So making that substitution, we get dy by dx equals something times d0 by dx plus something similar. d0 by dx is 0, something times 0 is 0, so the whole thing's 0. So we get dy by dx is 0. And a similar argument, but making only one of the masking things mask go to 0 and the other one being the unary thing that you want, gives you the unary case. The general case, which is here, is obtained. We've got the case 0, 1, and 2, and then we proceed by an inductive argument. Some slightly non-trivial inductive argument. You can rewrite actually the general chain rule in a substitution way, and that's a pretty, I just wanted to put it in there because it's pretty. It seems less, yeah. So you just say that dE with some substitution by dx is dE by dx for all the arguments that you're substituting for dxi, and you do the substitution on that, having done the differentiation, and then you multiply. So it almost says that substitution and differentiation commute. Okay. The semantics is just what we'd expect, given that we're trying to axiomatize equality over the smooth functions. So we have 2 kinds of environments, each of the variables, rho for ordinary variables, phi for function variables, and phi of f must be a smooth function with the appropriate arity. The definition of the denotations are completely what you'd expect. So if you look at the last 2 lines, when you look at a function application, you use the function environment to find out what function to apply. When you get to partial differentiation, you see what function x dot e is denoting, differentiate it, and apply to whatever e prime is denoting. There's an assumption there, of course, that that denotation is smooth. So the definition is not prima facie proper, but you have, with an appropriate induction, you can show inductively the definition is proper and that function is smooth. And then you can define validity just to mean that E naught is valid. Well, I guess I should really say it's true that E naught equals E1 if they have the same denotation. So it's not so much validity, it's just truth in this particular model. Apologies there. Okay, consistency and completeness are pretty well what you expect. Consistency is straightforwardly provable. Completeness is what we want to prove, but we want to prove a strengthened form of completeness. In fact, we can prove completeness not only with respect to all smooth functions, but even just with respect to the polynomial functions, polynomially defined functions. So we say a polynomial function environment is one where phi of f is a polynomially definable function. And so polynomial completeness is if it's just that it's true that E naught equals 1 in all polynomial environments, function environments, then E naught equals E1. What's the strategy? How are we going to actually do this? Well, we're going to, as well, we don't quite go to normal forms, almost normal forms. We define things called canonical forms and show that every expression is provably equal to its canonical form, or to which we show available. We define a relation, equivalence relation between canonical forms, such that any equivalent canonical forms are provably equal. And then the crucial thing is to show this polynomial separation theorem that if two canonical forms are not equivalent, then they can be separated by a polynomial environment. And that gives you completeness, because you go through a contrapositive argument. If E and E prime are not provably equal, then their canonical forms are not provably equal. Then the canonical forms aren't equivalent, and that means they can be separated by a polynomial environment. That means they're not polynomially equal. And then you just go the other way around and you get, if they are polynomially equal, then they're provably equal. And since equivalence canonical forms is in the middle of that implication chain, and the last part you can make a circle using consistency, you have further that E and E prime are provably equal if and only if their canonical forms are equivalent. Now, the lemma that says you can get the canonical form is effective. So once we can show the canonical form is equivalent, then we would also get decidability, and they will be. Okay, so how are we going to separate things? How are we going to achieve the separation that we need? Well, let's go through some examples, and that'll pretty well show you the idea of the proof. So suppose, for example, I want to make g of f of g of x different from g of f of g of x, and I would like to do it with a polynomial. How are we going to do that? Well, it turns out all you have to do is number all the distinct sub-expressions. So x, I'm going to number 1. G of x, which occurs on both sides, I'm going to number at 2. F of g of x, I'm going to number at 3. F of g of x, I'm going to number at 4. And g of all of that, I'm going to number at 5. Then if you look in that, it says, for example, g of x, which is numbered at 1, has to be 2. So that gives you a condition g of 1 equals 2. And if you go around all the occurrences of g, you get, which are 3 altogether, you get another couple of equations like that, which you have to have. G of 4 is 5, g of 3 is 6, and a couple of equations for f. But Legendre's interpolation, was it Lagrange, Legendre? I've forgotten. I'll call it Legendre, may well be wrong. It's Lagrange. Anyway, so for g of 1 equals 2, to get that, you write this first summand. So when x is 1, then the multiplication there comes out to be 1, because you've got this normalization factor, 1 minus 4 divided by 1 minus 3. And so you get 2. That term vanishes when x is 4 or x is 3. And so it makes no difference then. But the other terms make the difference for each of those. And the thing's symmetrical. So you get what you expect. How about functions of several arguments? Well, it's exactly the same. So we write 2 trees there, just to make it clearer what we're doing, rather than that linear way of writing. So for example, if you take the left-hand tree, you can see that f of 3 and 4 ought to be 5. And the right-hand tree tells you that f of 1 and 2 ought to be 6. So this time we do multivariate interpolation. And instead of x minus something to see whether or not x is equal to the something, since the somethings are now vectors of length 2, what we do is we use Euclidean distance. But since we want polynomials, we take the square of the Euclidean distance. So for example, in the first term, we take the square of the Euclidean distance of x from 1, 2, and divide that by the square of the Euclidean distance of 3, 4 for 1, 2. So when x is 3, 4, well, again, that'll all come out to 1, and we'll just get the 5. When x actually is 1, 2, that'll be 0 as we want. Okay, that's fine. But we have partial differentiation. How does that affect things? Well, a little bit of notation. We want a bit of notation for iterated partial differentiation. So this is a case of a binary function. We can differentiate the first or second argument. So indicate that by indices 0 or 1. So if m's a sequence of zeros and ones, that means differentiate. Well, the last one is the first thing to differentiate. So if it's, for example, d01, that's dx0 by d1 of f. And we're applying that to x0 and x1 in that case. So we have a standard notation for iterated partial differentiation. I suppose we now want those two expressions to be different. Well, we just regard the iterated partial differentiations as functions, and which they are, but I mean symbolically. And we write trees like that, and we get some interpolation conditions as before. For example, for iterated partial differentiations of f, we have d01 of f at 3, 4 is 5, and d11 of f at 1, 2 is 6. So now we have to do interpolation, but with partial differentiation. And luckily, that is possible by a theorem of Severi in 1930, that any such problem is solvable by a polynomial. It's an amazing theorem. This is the multivariate case. The univariate case was done previously by Hermite. That's why it's called Hermite interpolation. And this is just a general statement of Hermite interpolation. If you have a set of points or nodes, as they call it, xi in d-dimensional space, and for each node, finitely many iterated partial differentiation conditions in a function f, then there is such a polynomial. And a proof is explicitly given in this easily accessible book by Lorenz. But there's one more issue, which is that we have polynomials as well as all these other issues. And so we have to deal with them. So we work with polynomially layered expressions. And here's a couple of them, the polynomials in red, the function symbols in blue, and you can see the polynomials and the functions alternate. The inputs of the polynomials are the outputs of the functions, and the inputs of the functions are the outputs of the polynomials. So the polynomials, once we've got their inputs, the outputs are determined, of course. So we want to make the outputs of these two occurrences of the polynomial p different. And notice these are essentially different polynomials because their inputs, f and g on the one hand and g and h of various things, are different. So the polynomials there are, as it were, p of xy and p of uv, where xy and uv are different variables. So we have to get the variables right. These are called the interpolation variables. But once we get them right, we get a bunch of polynomials that we have to make different. And we can always make a bunch of different polynomials different with suitable inputs. And then once we have all those reals, that'll give us the interpolations that we need. For example, if you look at the f there in the top left, then its output is going to be the input of p, the first input of p, but we'll know that. And its input are going to be, actually, they're going to be the same thing twice, namely the output of the q's. So we'll have a couple of numbers coming in and a number going out, but we can all solve all such interpolation problems, even when the f's are partially derived, so we can make that work. This just is a scheme for doing that, which shows you in more detail the kinds of things you have to do. First of all, you look at all the atomic expressions. Those are the ones which are just applications of functions, f of q of gx, and so on. We include the variables. These are going to become, as it were, variables for interpolation. So we call them interpolation variables. So we assign new variables to each of these, v1, v2, and so forth. Once we know them, we know how to get a polynomial. So p has the f, which is assigned variable v1, and the g thing, which is assigned variable v3. So we look at the polynomial p of v1, v3. We get all our nodes or interpolation polynomials that way, and that gives us the polynomial differentiation problem we have to solve. And off we go, we solve it, we get interpolation conditions, and that's how we do things. So let's spell out a little bit how we do canonical forms and atomic expressions. So atomic expressions, well, first of all, we need some symbolism. F sub m for repeated differentiation. We make the m a sub rather than writing d sub m f for no particular reason. And so we say a variable as atomic expression, and the application of f to canonical expressions is an atomic expression. That's following the same pattern as before. And we say if we have a polynomial and we substitute atomic expressions in its variables, then we get a canonical expression. And we have this canonicalization lemma that every expression is provably equal to a canonical form, as I mentioned before. Now, how about equivalence of these things? Well, first of all, we define equivalence of atomic expressions and any variable equivalent to itself. And if we substitute equivalent canonical expressions, or that in equal function applications, then they're equivalent as long as the two m's are just permutations of each other, because we can do partial differentiations any order we like. Now we have this equivalence relation. We can define equivalent. We can assign to every equivalence class of atomic expression interpolation variable v sub equivalence class of A, and we can use that to define the node polynomials, these interpolation polynomials we had a moment ago. So for any canonical form P of the A's, we just make the interpolation polynomial P of the V's. And then we say two canonical forms are equivalent if their node polynomials are equivalent in the usual sense of equivalence of polynomials. That you can prove them equal by the ring axioms and using the multiplication and addition tables. So then, using the techniques that we exemplified in the previous discussion, we prove this separation theorem. That's the main theorem, that given any finite set of canonical forms is a polynomial function environment which separates any two inequivalent canonical forms in that finite set. And that gives us immediately polynomial completeness, as we said, and a little bit of extra work, which is very nice. Of course, that's the main theorem, but we want to go a bit further. So we also get that two canonical forms are equivalent as it should be just equivalent, not provably equivalent, if and only if they're provably equal. So now I'd like to show decidability in something else like almost normal form in my remaining few minutes. So let's revisit the definition of equivalence and improve it a little bit. So this is exactly the same definition of equivalence of atomic forms as before, except we no longer ask for the canonical forms to be provably equal, but to be equivalent. But you know from the previous result that that's the same thing. So this is an equivalent version of equivalence of atomic forms. And it's now in a form that obviously you could push through an inductive proof from the sum of the sizes of the atomic forms, that if you can decide equivalence of canonical forms, you can decide equivalence of atomic forms. You can also push through a proof that you can decide if two canonical forms are equivalent, then you can prove that just using the ring axioms, the addition multiplication tables, and the fact that you can do partial differentiations in any order you like. So in other words, we've missed out three of the axioms for partial differentiation: the chain rule and how to differentiate sums and products. Corresponding thing for canonical forms says, well, previously we had this very large global assignment of interpolation variables which you need for the proof. We can do a local assignment as well, or instead. So we think of two canonical forms. We think of their atomic forms, or so-called immediate atomic forms, the A's and the A primes. We figure out what their equivalence classes are with respect, and then we assign to each equivalence class just of that finite set and a variable, a new variable, and then we look to see if those resulting node polynomials are equivalent. This, in fact, is not doesn't need anything. It's just an immediate variant in the definition. It's a trivial variation in the definition. The thing is, it's suitable for proving decidability, because what you do is you look at the atomic sub-expressions, you decide that what the equivalence relations hold, then you can form the equivalence classes, you form the new variables, and you can decide polynomial equivalence. So we can push that inductive proof through, and you can also push the other inductive proof through. And that gives us two theorems with which I'll conclude. The first one is decidability. It's decidable whether or not two expressions are provably equal, and I'd like to know the complexity of that, and I have no idea how to go about finding the complexity of that. Another result, which I've essentially announced, is let's say two expressions are provably equal if you can do so without using the first three axioms of partial differentiation. And this says that for any two canonical forms, they're provably equal if not if they're canonical, if they're equivalent, if not if they're provably equal using this these limited abilities. In fact, you can improve that a little bit because you can go a little bit more normal. We can put the partial differentiations in a standard order, and we can multiply out the polynomials to get sums of distinct monomials. And then with that resulting stronger version of canonical form, then for provability, you only need additions, axioms, namely commutativity and associativity. So thank you for your attention over quite a long time, and I hope it was worth your while doing so. And I look forward to discussion on Tuesday.